We know that if we take any weak acid with the general formula HA and we mix it with water, it's going to be in equilibrium to form its conjugate base and H3O plus. And we know we can go further and get our dissociation constant Ka and its mass expression, which is H3O plus times the conjugate base divided by the weak acid, right? And of course, we can go further and call out H3O plus specifically. And H3O plus is going to equal to our Ka value times the ratio of our buffer components, which is going to be our weak acid divided by its conjugate base. And guess what, folks? We can make these values a little bit easier to deal with by taking the p-scale. The p-scale is equal to taking the negative log of whatever number you have on both sides. So if I take the negative log of H3O plus, I'm going to get pH. If I take the negative log of Ka, I'm going to get pKa. And if I take the negative log of this ratio, I'm going to get plus the log of now my conjugate base divided by my acid, or the base divided by acid here. And this brand new equation is called the Henderson-Hasselbalch equation. And as you can see, it does one thing: allow us to solve directly for the pH instead of having to calculate the H3O plus concentration, right? So no longer do we have to calculate the H3O plus concentration. Now we can go ahead and get the pH. So if we're thinking about the previous example, sure, you might have to go ahead and get a rice table for initial amounts. And then of course you have to get the changed initial amounts after you add an acid or after you add a base, right? But for that third rice table, you won't have to complete that third and final rice table if you use the Henderson-Hasselbalch equation, because you simply can take your new initial amounts for your base and your acid, take the Ka value, and of course get the pKa value, and then you'll automatically get pH. And of course, we'll go into a couple of examples of that as well. Another thing is sometimes you could just have an equation that already gives you the base and the acid and the Ka value, and you simply just plug it into the overall equation. So we'll be able to get to see a couple of those examples as we go along. We can then categorize the effective buffer ratio on buffer pH, as you see in this little mini table here. So our pH is going to be directly proportional to this new buffer ratio, which is our conjugate base divided by our weak acid. So if we're going to add more acid than conjugate base, then as you can see, since our weak acid is now in the denominator, this means it's going to be less than 1. And so the log of a number that's less than 1 is going to be negative. So the pH is going to equal the pKa plus that negative number. And what results is that your pH is going to be a smaller number than your pKa. Why would that be? If your pH is a smaller number, that means it's going to have a higher amount of the H3O plus. That makes sense because we have added a lot of our weak acid here. If we add a lot of our weak acid, that means we're increasing that H3O plus concentration, right? And so our pKa value would be larger because our conjugate base would be increasing as well, since we're increasing the HA concentration. On the other side of it, if we're going to add more base, for example, then our ratio of conjugate base to weak acid is going to be greater than 1. And so the log of the number is going to be greater than 1 or positive. And so your pH is equal to pKa plus a positive number. Therefore, your pH is going to be a larger number and your pKa is going to be a smaller number. And that again makes sense, because if you have a lot more of your base, then that means that you have a lot more of your conjugate base here. And so therefore, the equilibrium is going to shift to have more of your weak acid. And therefore, the H3O plus concentration is going to decrease. If I decrease the H3O plus concentration, I'm therefore going to increase my pH value, which is why it would be larger. So essentially, as we saw before, if I add more acid, I can decrease my pH. If I add more base, I can increase my pH. And if my weak acid and my conjugate base are equal, then that means my ratio is equal to 1. And if I take the log of 1, that equals to 0. So my pH is then going to equal to my pKa value. So let's go ahead and look at some examples using the Henderson-Hasselbalch equation. And remember, we only use this equation for buffer-based calculations only. So first up, we're back at the compound, and it says calculate the pH of a buffer that is 0.225 molar HC2H3O2, another way to write acetic acid, and 0.162 molar KC2H3O2, another way here to show that we're dealing with a salt that's going to dissociate. Of course, we're going to dissociate to our K plus, Go ahead and write that out. K plus, and then our acetate ion, C2H3O2 minus, okay? And of course, K plus is a part of a strong base, and so K plus is just spectator, does not react with water. It also gives us the Ka for acetic acid, which is 1.8 times 10 to the negative 5. So what we want to do is use the Henderson-Hasselbalch equation to be able to answer a simplified question like this. Again, they already give you the amount of the weak acid in its conjugate base, and they already give you a Ka value. So all you have to do is plug and chug at this point. Okay, so pKa is equal to negative log of whatever the Ka value is. They gave us this Ka value of 1.8 times 10 to the negative 5. So we can figure that part out. Log of the conjugate base. They already gave us this as 0.162 molar. How do I know this represents a conjugate base? Because the K plus does not react, so we know it's only going to be the weak base here from this weak acid that's going to be used. And then we're going to divide that by the weak acid, which is already given at 0.225 molar. So once we go ahead and get our pKa value, we can plug in all of our numbers and solve for pH. So pH is going to equal to negative log of my Ka value plus the log of 0.162 divided by 0.225. So the negative log of 1.8 times 10 to the negative 5 is 4.7. Plus the log of 0.162 divided by 0.225 is equal to 0.72. And so pH is equal to 4.7, and then when I take the log of 0.72, I get negative 0.14. So it'll be 4.7 minus 0.14, which equals 4.6. Why is there only one decimal place? Because there's one decimal place when we subtracted these two numbers. Now, of course, our concentrations that were given are 3 significant figures. So technically our overall pH should be 3 decimal places, but for this answer choices, they did not give us 3 decimal places. So we'll just go with strictly 2. And so if I have 4.6 here, I'll just add a 0 to get 4.60, which will be letter E. And so this is like if I'm already given this information and I'm just using the Henderson-Hasselbalch equation and just plugging and chugging. Now let's go ahead and see what it'll look like in another type of example. So here it says, consider a buffer that is prepared by mixing 0.30 moles of NH3 and 0.20 moles of NH4Cl in enough water to yield 500.0 milliliters of buffer solution. So we're creating this buffer solution by mixing this weak base with its conjugate acid. How do I know it's a conjugate acid here? Well, Cl minus is going to be an ion that does not react with any kind of water. So of course, that means we're going to be left with NH4 plus here as our conjugate acid. It says, calculate the pH after adding 0.03 moles of KOH. We know K plus does not matter, so it's really OH minus here. So now we're adding in a strong base to this buffer solution, and they want us to calculate the pH. When we did this before, we know there was a lot of rice tables involved, right? But this time, we're going to be able to use the Henderson-Hasselbalch equation. We'll talk about how to get through that. And it also says, assume the change in volume, yes, right, due to the addition of KOH is negligible. So now we don't have to go through dilution equations or anything like that, because any addition of KOH is not going to cause a huge change to the volume, so we're still going to be using the 500.0 milliliters here. It also gives us the Kb, which is the base dissociation constant for NH3, and that is 1.76 times 10 to the negative 5. And we can use the Kb to solve for Ka and then use the pKa in the Henderson-Hasselbalch equation. So what do we need to do? We need to get our initial concentration amount based on what's given. We also need to get the concentration of OH minus added. And then of course we need to set up a rice table. After we have our rice table set up, we can go directly into using the Henderson-Hasselbalch equation. And once we get our Ka value. Okay, so first things first, we're going to take our volume, which is the total volume of the buffer solution, and we're going to put it into liters. That way we can take our moles that are given of our base in its conjugate acid and of our OH minus, and we can get our molarity for the initial amount, okay? So we have 0.30 moles divided by 0.5 is going to give us 0.60 moles. That's the initial concentration for NH3. Then we have a 0.20 divided by 0.5 is going to give 0.40 moles. That's the initial concentration of NH4 plus. Then we're going to have 0.03 divided by 0.5 is going to give us 0.060 molarity, which is going to be the concentration of OH minus that's added to our buffer solution. So number 2 is going to be creating a rice table so that we can put all of our initial amounts onto that table. Now the question you have to ask is, what is going to mix with OH minus in order to get rid of it? And the only thing that's going to mix with this base is the conjugate acid. So we have to have our NH4 plus, mix it with OH minus. It's going to completely use up that OH minus and produce water and NH3. So I'm going to just go ahead and fill out all of our initial amounts. We have 0.40, we have 0.060, and then we have 0.6. We fill out our rice table, and we know that at equilibrium, the OH minus is going to be used up completely to 0. That means that the X value has to also equal 0.06. And so therefore, I can substitute X here and here. So when I look at my equilibrium amount for NH4 plus, after I've added OH minus, I'll take 0.4 minus my 0.06, and I get 0.34 molar. This is now my new initial amount here. I'll do the same thing with NH3 because water does not matter for us in our rice table. So we have 0.6 plus 0.06, which is going to equal 0.66 molar, our new initial amount for NH3. Now, instead of going forward like we did before to do another rice table, we can simply use the Henderson-Hasselbalch equation in order to be able to get pH. First, we have to be able to use our Kb value to get Ka, and then be able to fill out all the variables for the Henderson-Hasselbalch equation. Okay, so we have pH is equal to pKa plus the log of the base divided by an acid, okay? And so again, you know this is a conjugate base and of course the weak acid. But because we're dealing with the buffer, it's just going to be base divided by acid, because our acid here is still going to be NH4 plus, which still is considered a weak acid because it's a conjugate base. Okay, folks? So just make sure that you understand that little bit of logic. Now, for the A minus amount, we already have our base amount, which is going to be 0.66 molar. We already have the weak acid amount, which is going to be 0.34. We can figure this portion out. Now we need to consolidate pKa. Well, Kw is equal to Ka times Kb. So if I want to solve for Ka, I'm going to take my Kw divided by my Kb value. So that's going to be 1.0 times 10 to the negative 14 divided by 1.76 times 10 to the negative 5. I get a Ka value of 5.68 times 10 to the negative 10. If I take the negative log of this Ka value, I then get my pKa. So the negative log of 5.6 times 10, 5.68 times 10 to the negative 10 is going to be 9.24. So now I successfully have my pKa value, I have both my base and my acid value, and I can go ahead and solve for pH. Now I can say my pH is equal to 9.24 because I got my pKa value plus the log of 0.66 divided by 0.34. So when I divide these two numbers and take the log, I get 0.29. Okay, so it's going to be my pH is equal to 9.24 plus 0.29, which is going to equal 9.53. So of course, this is a way faster way to get to pH versus having to do multiple upon multiple rice tables like we saw before, folks.